astrophysics, and there's a heavy electron called the muon, and so we'll talk a little bit about it. Those will come up, so I thought I should mention them. So let's talk about cosmic rays now. So we know what neutrinos are, so what are cosmic rays? So cosmic rays are high energy particles from outer space that bombard the Earth, protons, gamma rays, and neutrinos. The astrophysical sources of the very highest energy cosmic rays are not understood. And so that's what we're trying to do, is to understand where are these particles coming from that are bombarding the Earth. So in 1912, Victor Hess went up in a balloon with some detectors, and he was measuring these particles that were hitting the Earth. They could do that on the Earth, and he was trying to see what would happen if you go up. Everyone thought that as you go up, you would see less, because they all come from the Earth. But no, he found as you go up in the atmosphere, they get more. Those were the cosmic rays. They get through the atmosphere somewhat, but they get more as you go up. So there are sources of cosmic rays that are from the sun, from our galaxy, and from outside of our galaxy. And so cosmic ray sources, so there's the sun, and the sun gives you cosmic rays that are less than 10 to the 10th electron volts. That's the unit of energy. It's the energy that an electron gains by going across a 1-volt battery. Okay, it's not very much energy, but 10 to the 10th is starting to get big. But the high energy cosmic rays from exploding stars and black holes in the galaxy can go up to 10 to the 12th or 10 to the 15 electron volts. And the very highest energy cosmic rays are from supercosmic accelerators outside the galaxy. This is what we want to look for. They're in the 10 to the 15th to 10 to the 20th EV range. So here's where the sun, this is a solar flare. The magnetic fields from a solar flare can accelerate protons, and we can get these 10 GeV protons that hit our Earth. One of the big sources in the galaxy of cosmic rays are exploding stars, the remnants of what we call supernovas. They can accelerate particles. Here's a simulation of a jet coming out of a supernova, and you can see that this is moving, and this is a slowed down version, moving very rapidly, and it can accelerate particles and make these cosmic rays that are hitting hitting Earth. But the most powerful accelerators in the universe are active galaxies, where we have a supermassive black hole at the center of a galaxy. Our galaxy has one, but these guys have huge accelerations, and they have these jets of particles that come out along the axis of the galaxy. How do these things come about? Well, they come about because black holes or neutron stars, they're powered by large gravitational energy as things get sucked in. So you end up getting a circulatory motion, and you can accelerate these protons to very high energy. They then can hit the radiation and dust, and that's what's going to make the cosmic rays. Protons and electrons, those curl up in the magnetic field, but the gamma rays and the neutrinos come straight out. So we can look back at where the neutrinos came from, and that's what we want to try to do. Okay, so these ultra-high cosmic accelerators, to get to this very high energy, you need very large objects with very large magnetic fields. And this is a plot of the size of an object, don't worry about all the different units, and the magnetic field, which is in Gauss, maybe that you know that. But if you look at all the kinds of objects, white dwarfs, these active galaxies, supernova remnants, radio galaxies, none of them have the properties that can get us up to this. So we have no good candidate for these really high high energy things, and neutrinos can probe inside these objects, because remember, a neutrino doesn't interact very much, so it can come out of these objects and tell us what's going on. So neutrino astronomy comes about because neutrinos are great cosmic messengers. They're electrically neutral.